Hello everybody and welcome to another Mac Deep Dive video. Today's topic is the Apple M series elusive matrix coprocessor aka AMX. Back in 2019, when Apple announced the A13 Bionic, it included a low-key mention of a new accelerator specifically for machine learning. Based on the keynote slide, it appeared as if two SIMD units for accelerated matrix operation were incorporated into the CPU itself, which Apple claimed to have increased the matrix multiplication power of A13 Bionic by 6 times, allowing the CPU to achieve 1 trillion operations per second. With the debut of the M series Mac chips in 2020, it became apparent that they too come with a new accelerator, which is no less than a dedicated processor optimized for matrix computations. It soon came to be known as the Apple Matrix Coprocessor, AMX. AMX is a so-called outer product engine, and it operates differently from discrete accelerators such as GPUs. Unlike the latter, it directly interfaces with the standard instruction stream fed to the CPU cores that decode the special instructions. This approach eliminates the necessity for explicit memory management and instruction buffering associated with GPUs, thereby significantly reducing computational latency, which is particularly critical for small matrix computations. In the beginning, the AMX coprocessor was not directly exposed through a dedicated API. However, Apple's Accelerator framework would silently dispatch suitable workloads to the coprocessors, delivering significant speedups. A close examination of the instruction data revealed that there are new undocumented instructions being processed by the M series chips. Apple made a non-standard extension to ARM's instruction set, which ultimately formed the basis for ARM's Scalable Matrix Extensions, aka SME, which was first announced in mid-2021 as part of the ARM v9 architecture. Finally, in 2024, with the debut of the M4 chip, Apple officially introduced support for ARM SME instructions, allowing third-party developers to write code that target the M series matrix coprocessor. Thanks to an abandoned patent from Apple, we now know that the AMX instructions operate on a 32 by 32 grid of compute units. Each AMX unit is capable of performing 16-bit floating-point multiply-accumulate operations. The architectural design enables flexibility in operand size. 32-bit operands are handled by arranging the compute units in 2x2 subgrids, while 4x4 subgrids can handle 64-bit operands. This structure enables a single instruction to perform a full outer product operation, multiplying every element of an X vector with every element of a Y vector and accumulating the results into the Z matrix. In this annotated die shot of the M3 Max chip, the AMX units are shown in red. There are two big AMX units co-located with the P cores and one small AMX unit in the E core cluster. The big AMX unit is 60% the size of a P core and double the size of the small AMX core. The overall silicon budget allocated to AMX coprocessors is under 2 P core equivalents. To appreciate the benefit brought about with the AMX accelerators, let's look at the max theoretical throughput of the 4 neon vector units present in every P core. In FP32 or single precision, each neon unit will process 2 16-byte operands and produce one 16-byte result composed of 4 FP32 elements. Spread over 4 neon units, that's 16 FP32 values per cycle, or with fuse multiply add on top of a previous result, 32 FP32 floating point operations per cycle. Therefore, one P core processes 32 single precision inputs and produces 16 single precision outputs per cycle. The AMX coprocessor has two 16-element long vectors as inputs for a total of 32 FP32 inputs. However, the outer product computation results in an output matrix of 256 FP32 values per cycle, or 512 single precision fuse multiply add operations per cycle. That's 16 times faster than a P core for the same amount of input data. Based on this, we can expect the two AMX coprocessors to easily outperform the 12P cores in FP32 matrix multiplication. The ability to perform that many more operations with the same amount of data is critical to reducing the energy consumption of a computational device, as nowadays the energy needed to transfer data significantly exceeds the energy needed to perform computations on the data. An outer product is a way of multiplying two vectors that produces a matrix. The idea is to multiply every number in the column vector A with every number in the row vector B. One way to do that is to take the first number of B and multiply every number of A. This becomes the first column of the result matrix. We repeat the same with the second number of B to produce the second column of the result matrix, and likewise with the third number of B. The outer product way of multiplying matrices is unlike what is typically taught in school, where each element of the result matrix is computed by multiplying a row in the matrix A with a column in matrix B. In other words, the multiplication of two vectors produces just one value. This is highly inefficient because we would be reading the same rows and columns over and over from memory. With the outer product way, we load a column of A and a row of B only once and compute the matrix of results instead of a single value. It works as follows. Take each column of A and pair with the matching row of B. Compute their outer product, the result of which is a matrix. Sum or accumulate the three resulting matrices to complete the matrix multiplication. It takes 3 cycles to multiply a 3x3 matrix this way. Apple's outer product engine accelerates both the outer product calculation and the matrix accumulation. Let's take a look now at the performance of AMX. In this test, I benchmarked the matrix-matrix multiplication compute bandwidth in single precision floating point for a range of square matrix dimensions from 32 to 8192. This is a log-log plot where each tick is double the previous one. In ideal conditions, the M4 Max has a theoretical computational bandwidth of 4 teraflops. Remarkably, AMX on the M4 Max is able to effectively reach its theoretical maximum, albeit only for one particular matrix dimension. For large matrices, the performance stabilizes at around 3.2 teraflops. For small matrices, the performance is far below the theoretical maximum. Apple's BLAST library that ships with macOS is not particularly well optimized for small matrices. Therefore, I want to see how a library specifically optimized for small AI workloads would fare instead. I settled on libxmm from Jena University, Germany. This library just-in-time compiles compute kernels for a wide range of architectures, including ARM's SME instructions supported by Apple's M4 series silicon. And what a difference it makes! The performance for square matrices of size 32 is a whopping 3 times greater compared to the BLAST library. However, for matrix sizes above 64, the BLAST library takes the lead. Therefore, for optimal performance across the full range of matrix sizes, the computation would need to be dispatched accordingly to the best library implementation. It is well understood that GPUs excel at matrix arithmetic. The M4 Max comes with a beefy 40-core GPU. How would the AMX engines fare against this GPU, do you think? The results might surprise you. For matrix sizes up to and including 512, AMX is vastly superior to the GPU. For matrices of size 32, it is 1,000 times faster. For matrix dimension of 768 and above, the GPU takes the lead, but it only reaches its peak performance for matrices of size 4096 and above. This is roughly 85% of its theoretical maximum throughput. Therefore, the optimal performance on the M4 Max will be achieved by using AMX for small matrices and the GPU for large matrices. Apple's machine learning library MLX allows the programmer to very easily target either the GPU or the AMX engines for a given computational kernel. Looking from this angle, we can see that Apple used the extra silicon for the AMX engines to offer optimal performance across the full range of problem sizes. Computational throughput on small matrices is not AMX's only advantage. In fact, it is significantly more power efficient than either the CPU or the GPU. In this table, I've compiled the peak performance and power draw for the AMX engines on the P-core and E-core clusters. Compared to the Neon units in the P-cores, the AMX engines provide 2.75 times the performance and 10 times the G-flops per watt. The two AMX cores achieve the same level of performance as the Ryzen 9950X, but at almost 6 times less power. While the GPU provides far superior performance for large problem sizes, the AMX engines are nonetheless 45% more power efficient than the GPU. In fact, according to my testing, Apple's GPU does not compare favorably in power efficiency even to Nvidia's last-gen RTX 4090, trailing it by 23% in G-flops per watt. According to Apple's 2025 September 9 event, the A13 GPU cores come with neural accelerators, which offer 3 times the performance of the preceding generation's cores. This might mean that a hypothetical 40-core M5 Max GPU would achieve at least 43 teraflops in dense matrix multiplication, and potentially more if the GPU clock speed goes up. That would put it at near RTX 4090 level and make it far more usable for local LLM due to a corresponding uplift in prompt processing performance. The AMX engine on the E-core cluster performs nearly as fast as 3 P-cores, but its power draw was so low that it would not even register on my power meter despite its 0.1 watt resolution. If we look at the die shot of the M3 Max, that of the M4 Max was never published, we can observe an even more staggering efficiency advantage of the AMX engines. While constituting only 2.5% of the GPU in area, they achieve 29% of its performance. In other words, over 11 times more performance per millimeter square. While the GPU on the laptop and desktop Apple Macs is more powerful than the AMX engines, that is not necessarily so on iPhones. According to my estimate, the peak performance of the AMX engine exceeds that of the 5-core GPU on the A13's SoC. Judging by the fact that the M4 Max GPU achieved only 85% of its peak performance in matrix multiplication, even the 6-core GPU on the A18 Pro might fall short of the AMX in this scenario. Moving on to memory bandwidth. In my testing, the AMX engines consistently equal the P-cores in achieved bandwidth. It appears that they both share the same L2 miscue and can attain 400 GB per second in a balanced read-write workload. As in the previous video, I again examined the matrix vector multiplication kernel. In this roofline plot for the M4 Max's AMX engine, we can see that the kernel lands in its memory bound region. Compared against the GPU, in this memory bandwidth test, the AMX extends its lead even to medium-sized matrices. For small matrices, the performance gap is staggering, with AMX being over 500 times faster than the GPU and reaching 850 GB per second thanks to the matrices fitting within its L2 cache memory. It's very important to note that in this test only a single AMX engine was used. Apple's Accelerator library elects not to use the second AMX engine for the matrix vector multiply kernel. Nonetheless, a single P-core can execute 2 128-byte loads per cycle from the L2 cache, double that of the Zen 5 core, which explains the impressive showing here. The performance stays at this high level for square matrices up to and including 1536 in size, which is roughly 27 megabytes in memory, consistent with previous assessments that the M4 Max has a 32 megabyte L2 cache. However, for large matrices, the GPU takes the lead and performs twice as fast, attaining 510 gigabytes per second, which is quite close to the chip's theoretical max bandwidth of 546 gigabytes per second. The compute and bandwidth tests gave us a pretty good picture of what Apple had in mind by introducing yet another type of processor to their system on a chip. The AMX dramatically outlets performance precisely where the GPUs have been traditionally weak, small problem sizes which are overhead dominated. Furthermore, AMX delivers superior power efficiency, particularly so if used on the E-cores, at a cost of performance. Given a choice between AMX and Neon, there is hardly any compelling reason to use the latter in linear algebra workloads, as it delivers inferior performance at a much higher power draw. Thanks to M4 chip support for ARM's SME instructions, third-party developers can finally target Apple's AMX coprocessors and deliver performance superior to Apple's own linear algebra libraries, as we observed with the library from Jena University. What do you think? Leave your thoughts in the comments below, and if you enjoyed this video, don't forget to click like and subscribe to the channel. See you next time!